engineering cohorts. Founded in the year 2001, Don Bosco has been providing quality education for 15 years now and currently offers 7 undergraduate courses, 8 postgraduate courses, and 3 research centers for pursuing doctoral programs. The Bachelor in Economics. After all, Karnataka itself has over 200 of them. Picking the right one can greatly enhance your learning, life experience, and even job opportunities after the course. In the next few minutes, you will see how and why Don Bosco Institute of Technology is the college that is designed to make you a successful engineer. Founded in the year 2001, Don Bosco has been providing quality education for 15 years now and currently offers 7 undergraduate courses, 8 postgraduate courses, and 3 research centers for pursuing doctoral programs. The Bachelor of Engineering course is as much about learning via hands-on experiments as it is about theory. Don Bosco focuses on providing students the best of laboratory facilities to complement the able faculty and the university curriculum. In fact, given the superior status of our infrastructure, the university and the regulatory body, AICTE, has approved an impressive 740 seats for the engineering program. This high number itself is a testament of the number and quality of equipment available to our students.
I see the startup world on industrial wisdom labs in India on product innovation, incremental innovation, or business model innovation. Keeping in mind we are planning to make Don Bosco Institute of Technology not only a quality institute but also the leading university coming years.
Across different specializations, the college employs experienced faculty who undergo the faculty development courses so that students always get the best of teaching. For instance, the Computer Science and Engineering Department has 40 faculty members, and some of them are pursuing research alongside teaching. The results of such a focus on experienced and skilled faculty is telling. Currently, 80% of all students who enter the engineering courses complete the course successfully. The figure is higher than the average. In 2013, the university's 6th rank in Information Science and Engineering was backed by Don Bosco students. While technical education is most critical in an engineering course, Don Bosco recognizes the need for creating an atmosphere where all-round personality and life skills development can happen alongside the technical course. The college spans an impressive 36 acres and gives students opportunities to pursue a variety of sports like softball, kabaddi, badminton, wrestling, judo, and athletics. Don Bosco students have won several awards in recent years in all of these sports at university level. This to help students relax both mentally and physically. At Don Bosco, several cultural events are held throughout the year. The annual Intercollegiate Fest of Don Bosco being held on a large scale with much pomp is popular and sought after amongst engineering colleges in Bangalore. This year, the event saw celebrity performances and a DJ night for the students. Apart from this event, there are regular inter-college cultural technical events held throughout the year.
The united mind view the most powerful resource is learning. To become a center of excellence, to build an innovative research environment, to match the growing needs of society and industry, by creating relevant infrastructure, quality human resource, essential to empower future professionals.
have to just take our word for the excellence in teaching and facilities. Take one look at the corporates who associate with us or offer jobs to students straight out of Don Bosco, and you will know that the college is respected in good circles. Intel, Microsoft, Oracle, Siemens, and Bosch are some of the companies that associate with Don Bosco to run academic programs and offer jobs to our students. Other recruiters include the who's who of the technology world: Infosys, Tech Mahindra, Accenture, Cognizant, Samsung, and Cisco. Just few names amongst many. Hostel facilities are provided for students who come from outside Bangalore. The hostel is much more than a lodging facility. It is a full-fledged living arrangement designed to make students feel comfortable, with all basic needs taken care of, from in-house healthcare to a cafeteria with a variety of foods, from uninterrupted internet connectivity to reading rooms and TV rooms. The hostel has it all. Some students say the hostel is more comfortable than their homes.
The hostel of Don Bosco Institute of Technology is not just a place to stay, but also a place to relax, almost like home.
I love Don Bosco Institute of Technology because education is uncompromised here, but there is still lots of scope for sports and fun activities.
I'm very impressed by the extensive laboratories present in Don Bosco. It makes learning simpler and more effective. I think a good friend circle is very important in the college, and Don Bosco seems to have attracted some brilliant students, and therefore I have been able to make superb friends here.
Innovations happen when people of different backgrounds think together, challenge each other, and help each other take innovations out.
A very good morning to present one and all. Life is precious simply because it is a gift from God. Thank you, Lord, for another amazing day full of so many blessings. A river cuts through rocks, not because of its power, because of its persistence. A very good morning to everyone. Thank you to each and every one of you for being with us today. Myself, Krishna Veni, Assistant Professor, Department of Chemistry, Don Bosco Institute of Technology. I take the privilege to warmly welcome all our delegates on virtual Faculty Development Program on Advanced Functional Material for Science and Engineering 2023. I would like to formally welcome our respected President, Sir Bailappa Sir, Bionomic Education Trust, Bangalore. Honorable Vice President, Sir B. Manjunath Sir, Honorable Secretary, Sir Raghav Bailappa, and Dr. B.S. Nagabhushana, Principal DBIT, and HODs of various department, guest speakers, senior researchers, academicians, distinguished participants, and my dear colleagues. It is a great honor for me to welcome you all once again for 1 week faculty development program on Advanced Functional Material for Science and Engineering 2023, being organized by Department of Chemistry, Don Bosco Institute of Technology. Now I request Shreya from first year ISE branch to invoke the Almighty.
Namma Sharade Uma Maheshwari Nimmoda Gihanyaramma Namma Sharade Uma Maheshwari Nimmoda Gihanyaramma Kamma Golana Vairi Sutanana Sundila Kamma Golana Vairi Sutanana Sundila Hemmaya Gananathane Ammaya Namma ಶಾರದೆ ಉಮಾ ಮಹೇಶ್ವರಿ ನಿಮ್ಮೊಡಗಿಹ ನ್ಯಾರಮ್ಮ ಮೋರೆ ಕಪ್ಪಿನ ಭಾವ ಮೊರದಗಲದ ಕಿವಿ ಕೋರೆದಾಡೆಯ ನ್ಯಾರಮ್ಮ ಮೂರು ಕಣ್ಣನ ಸುತ್ತ ಮುರಿದೇಟ ಚಂದ್ರನ ಧೀರತ ಗಣನಾಥನೇ ಅಮ್ಮಯ್ಯ ನಮ್ಮಮ್ಮ ಶಾರದೆ ಉಮಾ ಮಹೇಶ್ವರಿ ನಿಮ್ಮೊಡಗಿಹ ನ್ಯಾರಮ್ಮ ರಾಶಿ ವಿದ್ಯೆಯ ಬಲ್ಲ ರಮಣಿ ಹಂಬಲನುಲ್ಲ ಭಾಷಿಗ ನಿವನ್ಯಾರಮ್ಮ ಲೇಸಾಗಿ ಸುಜನರ ಸಲಹುವ ನೆಲೆಯಾದಿ ಕೇಶವದಾಸ ಕಣೆ ಅಮ್ಮಯ್ಯ ನಮ್ಮಮ್ಮ ಶಾರದೆ ಉಮಾ ಮಹೇಶ್ವರಿ ನಿಮ್ಮೊಳಗಿಹ ನ್ಯಾರಮ್ಮ ನಿಮ್ಮೊಳಗಿಹ ನ್ಯಾರಮ್ಮ. Thank you.
Thank you, Shreya. Now I would like to share highlights about FDP. Don Bosco Institute of Technology was established in 2001 as a part of Dynamic Education Trust that envisions providing quality education in engineering technology and management studies. Presently, DBIT offers undergraduate programs in 8 domains that include computer science and engineering, information science and engineering, electronics and communication engineering, electrical and electronics engineering, civil engineering, mechanical engineering, artificial intelligence and machine learning, artificial intelligence and data science. Besides, the post-graduation programs in management studies entitled Master of Business Administration. 9 departments, including basic science departments, are research centers that offer PhD programs. All UG, PG, and research programs are affiliated to Vishveshwaraya Technological University, Belagavi. All eligible UG programs of DBIT are accredited by NBA, and the institution has NAC accredited. The quality of education at the institute level is governed by Internal Quality Assurance Cell, IQAC, whose progress framework percolates to the constitute departments in the graceful manner, so as to enable building quality into the system from the grassroots level. Specific to the context, the calendar of events at the institution level, which also get detailed out at the department level interface. Value-added programs into curriculum so that both the students and faculty get additional knowledge, which further help in knowledge generation in the hand of mature faculty and even senior students, even senior students through their research, which is an ongoing activity of our faculty alongside their teaching activity. Now I request our beloved principal, Dr. B.S. Nagmushna sir, to share few words and motivate us. Nagmushna sir, good morning sir. Principal sir.
Very good morning.
Please, sir.
Am I audible?
Yes sir, you are audible sir, sufficiently.
So very good morning to all of you. At the outset, it gives me a great pleasure to be a part of this 5-day online FDP on advanced functional materials for science and engineering on this inauguration day. So this particular subject on advanced functional material per se, so even the material science. So we have been studying material science as teachers. We have been teaching material science for many decades now. And the observation now is from the past 1 decade, so it has really taken a multiple dimensions of innovations, quest for new materials, and how to use these materials for different specific functionalities. We will not go to the details of this because anyway, the next 4 to 5 days, so we would have resource people from various universities, CSAR labs, and also many renowned academic institutions who have been doing extremely good work in this space. I take this opportunity to welcome all the resource personality, whoever are with us today and who are going to be with us the next 4 to 5 days. Secondly, the effort behind organizing this workshop, faculty development program, so goes to Department of Chemistry, steered by Professor Manjunatha. And I very sincerely submit my appreciation to Professor Manjunatha and his team, who have really struggled hard to line up very good speakers for this FDP program. So extending it further, so I also would like to express sincere gratitude to the Dynamic Education Trust, President, Vice President, and the Secretary for allowing us to conduct this workshop from today till 19th. Having said that, so we have, in terms of the participants, I understand that 220 people have, 300 people have registered for this online workshop. And that shows two things. One is the importance of the subject and the influence that it has made on the teaching fraternity and also the research community. Secondly, so conducting these FDP programs by way of conducting it online, so we are in a position to extend the outcome of these such workshops to a larger number, so rather than consolidating some number on campus, anywhere it is. So it has its own logistic and other difficulties. So owing to these two, so the FDP is having a high level of impetus, in my opinion. While I welcome all the delegates, the participants from different institutions, research establishments, and industry. So I wish them a good learning in the next 4 to 5 days, 5 days of FDP on this, topic of advanced functional materials for science and engineering. One sincere request before I close, that most of the workshops, what happens is, of course, we do have very serious researchers who would take it further with respect to their individual contribution or contribution as a team member in their respective institutions. So we see, we do have participants who get to a very busier schedule after this FDP is over. So I sincerely request that let us have such FDPs, not necessarily this FDP. And probably any of the FDPs that our teaching fraternity, teaching people are going to attend, to take it a little bit more seriously and then have a plan in place for moving further. So what I mean is, in specific, after this FDP is over, the faculty should really plan, what do I do with that? And the respective institutions also should encourage the teaching faculty, whoever has attended this, to really take it further. At least in Don Bosco, we are doing that. Any FDP, we would like to see the effectiveness of the FDP or the workshop or the value-added courses that our teaching faculty attend. So I sincerely urge that each of the participant who attends this faculty, so to have a great learning, because we have already lined up about 10 different speakers. Some are from industry, some are from CSIR lab, and some are from NITs and many renowned institutions like RV College, Siddharanga Institute of Technology, and professor from Bangalore University, and Christ University, so who incidentally is a good friend of mine. So we have lined up quite a few, and from Jain University, and 2 are from CSIR labs. So it is hard to get people, resource people who can really teach us intricate, the details about the topic on advanced functional material. So I would request, firstly, all the participants to have a great learning the next 5 days, and also have a plan in place after this FDP is over. On account of this FDP, I am going to do this activity. Maybe I define a project around that. Maybe I rerun this FDP with an augmented level of details into that, or I probably would rerun this FDP with some practical aspects in place. So this is basically, should be a train the trainer concept also. So from these perspectives, attending this FDP or any FDP for that matter becomes very important. I will not take much time. I wish all the participants a great learning, and at the same time, I am very grateful, and let me submit my sincere appreciation to the organizers and also the resource people who are on the call today, and also who are going to be with us the next 4 days. I sincerely thank the organizers of this workshop to give me an opportunity to speak a few words to all of you. Thank you.
Thank you, sir. Thank you so much, sir. The power that we have, the knowledge and the influence that we have are beautiful gift from God to be utilized to serve each other unconditionally. Now I would like to introduce our chief guest and keynote speaker, Dr. Palani. Dr. Parlipan sir is working as electronics and electrocatalytic catalysis division, CSIR, Sikri, Karaikudi. Sir has completed his BSc in 1991 to 1994, University of Madras. And sir has completed his MSc from Indian Institute of Technology, Bombay, in the year of 1995 to 1997. Sir has pursued PhD from Wayne State University, USA from chemistry. And sir has completed his postdoctorate fellowship in the year of 2006 to 2008, University of Massachusetts, USA, in the field of material science. And from June 97 to February 98, he worked as research assistant in R&D division, Draft Kettle Chemicals, Bombay, India. And March 28, March 98 to June 98, sir has worked as assistant manager, R&D division, Backlight Highline Limited, Hyderabad, India. And in the year 98, sir worked as a project assistant in PD division, National Chemical Laboratory, Pune, India. In the year 2000, from August, then February 2006, sir has worked as graduate student. He was a graduate student at Wayne State University, USA. And 2006 to 2008, sir was a postdoctoral fellow, University of Massachusetts, USA. And 2008 April and till date, sir is working as a scientist at the CSIR Sikri, Karaikudi. Sir has played a key role in many different areas, including synthesis and process modification of additives, method development, physical and chemical for analysis of additives, and quality check for both raw materials and finished project. Sir has published n number of papers and book chapters. With this short introduction, I welcome you, sir, once again.
Thank you.
Over to you, sir.
Thank you, Krishnaveni ma'am, for the nice introduction. I thank all the organizers, especially the Secretary Raghav Bailappa, Executive Director Manjunath, and your Principal Nagabhushana, and the Dean and Director Research R&D Nataraj KR, also Vice Principal Umar Shankar, and the organizer Manjunatha, Head of the Department, Head of the Chemistry Department. Thank you all for this opportunity. I will take probably an hour and a half and try to cover the important areas of research that we've been focusing on for the last, let's say, year or two. Now, the government of India is pushing more towards energy sectors and healthcare and water. We will discuss about the government of India has announced different mission program, and then we will talk about how we can address those programs using the supports of electrochemistry. And since I come from Electrochemical Institute, we will talk about it. So let me share my PowerPoint first, and then hopefully I'm audible also by now, right?
Yes, yes. Yes, sir, you are audible, sir.
Okay, good. So let me share the PowerPoint, and then let's go ahead from there. Okay, is this visible now?
Yes, sir, visible, sir.
Yeah, okay. So what I'm going to touch upon is I'll talk about the role of carbon-based functional materials in the development of electrochemical senses. I'll touch a little bit on water purification and talk more about healthcare industries, and little on energy sector where we work on something like oxygen reduction reaction or a hydrogen evolution reactions. But when it comes to energy, especially like batteries or supercapacitors, we have expertise, and it will be more appropriate that Dr. Satish from our CSAR Sikri will introduce those areas to the speakers. So I will touch upon mainly on two areas, water and then healthcare industries, and we'll talk about all these sensors that will work on it, right? Just 1 second. Yeah, hopefully the slides are moving, right?
Yes, sir.
Okay.
Yes, sir.
So, like if you look at it, please feel free to stop me anywhere. Don't worry about the number of slides or something like that. If you have any doubt, please feel free to stop and then ask at that point itself. You don't have to wait till the last minute. So, and it's good for both the students and faculty. Yeah, please. I guess most of you are also from a chemistry background and then little bit on engineering background, correct? Okay. Is it muted for the rest of the people? That's why they are not able to answer it, or? Okay. On a national mission, if you look at it, we have a national mission on transformative mobility and battery storage. And then the most importantly now, government is spending a lot of time and energy on green hydrogen mission. So that's helpful in terms of getting net zero emission. So that's how we will keep up this global warming in control, and that's why people are now started working on this hydrogen mission. And then of course, like not all the population in India have access to the clean water, right? So that is one of the important mission that we also have to worry about it. So that comes in what is called National Scholar Mission, Jal Jeevan Mission, and National Clean Air Program. So all this comes under that. And then we also have another program called Waste to Wealth, right? How to convert all these waste to wealth. So even my talk as well as Dr. Satish talk will actually give a glimpses of how we can convert these waste into useful material, using which we can produce, let's say, either a green hydrogen or supercapacitors, or even, for example, biosensors. So we'll touch a little bit on those areas also, and the rest, all the corrosion mission and rarer materials, it's all more related to our SICRI activity, and that's kind of what we put in CECRA, Central Electrochemical Research Institute. In a short, we call it as a SICRI, and these are like kind of the activity that we do take care in our institute. So if anyone is interested pursuing higher degrees, whether say postdoctoral degree or a doctoral degree on these areas, please feel free to contact any one of us, and we will help you or guide you on that particular part. Ma'am, still am I audible or?
Yes, sir. You are audible, sir.
Okay, so I'll just come to this particular part. We'll start with a very easy note, and then we will go into a little bit of more on chemistry. So we have only faculty, also we have some student members also there.
Faculty as well as some research students will also be, sir.
Okay, good, excellent. Okay, so I think this particular structures on your left side, right? This everyone must be remembering this particular structure, right? This is a structure of EDTA. This EDTA will go and complex with your first row metals, right, like a lithium and things like that. In a periodic table, if you look at it, the first row and second row, these normally goes and bind, especially they binds with, let's say, magnesium and calcium, and then we will find the water hardness using this particular material, right? Similarly, if you go into organic chemistry, we have pyridine molecule, right? If these pyridine molecules, like 3 pyridine molecule, if you put together, then they call it as a tripyridine. And because these nitrogen has got a lone pair, they can go and nicely bind with any of the metals, right? Why we are using this is, there is a mission where we need to clean the water, right? But not all the time we will have access to the electricity. For example, let's say if you're in a city life, you can think about it. Why you think I don't have access to the electricity? But there are times when there is a flood or there is an earthquake, some natural calamity occur where we lose access to the electricity. That is one part, right? The other part is there are still some rural areas of India. They are also still suffering to get electricity. Right now, it is actually almost reached, but there are still few parts. If you look at northeastern side, there are few areas where strategically there is no electricity is not being provided, and there are areas where people don't have access to that and electricities are not being provided. In those places, how do we clean the water, right? So if you look at it, the earlier days, people would have used what is called a gravity filter, and we will use the similar thing. But then what is the difference that we're going to put in, right? How do we functionalize the material and how that can be used for making a gadgets? That's the question that we start asking ourselves, right? So we have material called graphene. I will actually give a little introduction in the couple of slides, but I just wanted to start with a very easy note, like everyone can understand the importance of water. So we'll start with that. So how do we purify the water? We have a material called graphene. Onto onto the graphene, I will attach this particular material, what is called terpyridine. Now, what this terpyridine will do is, you see there are 3 nitrogens, right? Like a EDTA, they go and form a coordinate bond with the heavy metals. So in this way, you can remove a lot of heavy metals, let's say something that comes up from copper industries. Mostly it's going to be a copper, right? Because we have a lot of construction that is going around our areas, whether it be a Bengaluru or Karaikudi or Tamil Nadu, right? There are a lot of construction that is happening, and that real estate area is booming up, which means that we are going to produce more and more of carbon, more and more of iron, right? All these industrial metals goes and get accumulated either in a soil or into the water. So we need to remove that excess of that. So we use what is called this graphene that has been functionalized with the terpyridine molecule, right? So I'll talk about how do we do this chemistry also. You will understand as we go further on our talk. Now, just assume that I have functionalized the graphene with this particular molecule, terpyridine. Now, if I throw the water which has been contaminated with, let's say, iron or copper, they go and bind with this 3 nitrogen bonds, and you can easily remove them. Okay, so that is a one way where you can purify it. This is one example, very, very simple technique that we tried in our lab. I mean, you can just see that, the simplicity of this particular experiments. What we have done is we have taken a burette and then filled up the whole place with the carbon powder. And the carbon that we purchased also contains some amount of silver nitrate, so that it can also act as an antibacterial agent. Once you have a silver nitrate with all this, so you take this carbon and you convert them into either a graphene or use them as such. Either way, it is good. You functionalize using this complexing agent. So you get a terpyridine functionalized carbon powder, which also contain some amount of AgNO3. So the AgNO3 will act as a disinfectant, right? It acts as an antibacterial agent. So it kills off all the bacteria, and all your metals are being removed by the organic material that we added up. So what we have to do is we just have to do the gravity filtrations. Then you can see the water that comes out will be pure. This is just a small experiment set up by our BTech students, right? And we have analyzed the water quality. We started off with 1000 ppms of known copper chloride, and then iron sulfate, iron oxide, and things like that, right? And when we purify the water, we figured out from 1000 ppm we could reduce to, in case of copper, approximately 20 ppm, and in case of iron we've been reduced to almost 20 ppm. So it binds nicely with the iron compared to the copper, this terpyridine molecule. If you ask me, is there any selectivity? No, but whatever the heavy metal that is going to be present in the water, it all will be complexed with this copper terpyridine moiety, and then we can easily remove them. So I'll just go to the next slide. This few examples how that powder will look like. You can grind them, make them into porous material and things like that, right? And based on how you pack this column, the levels of impurity that we remove will vary, and there are a lot of trial and error method that we tried out it. Okay, so let's not worry about it. And there are another thing which probably I don't have this slide on with me. If you remember earlier days, we used to have a stainless steel what do you call vessel. There'll be 2 portions, one top portion, one bottom portion, and in that top portion you will have a ceramic candles, right? And you pour the boiled water into the ceramic candle in the night, maybe let's say around 10 o'clock, just before you go to the bed. And then if you look at in the morning, you will get 10 liters of purified water that been collected at the bottom. So even those ceramic candles can be functionalized with this carbon based material. Okay, once you functionalize the ceramic candle with this kind of carbon based material, you can get the water which is purified and free from all those pathogens, because it also contains some amount of silver nitrate or silver nanoparticle. Is that the only technique that can be used do the water filtration without electricity? That would be a next question, right? There are some gadgets that are commercially available, and most of them, I'm not trying to publish a particular brand, but these are available from, let's say, your Amazon, right? And the prices that I put in, actually you can see from the Amazon, maybe they are okay to clean 100 liters of water. It depends on how much of water can be purified with any of these gadgets. That's what it is, right? Once 100 liters of water is being purified, you need to change some component inside. So the same question you can ask, sir, can we reuse your candle or can we reuse your material that has been functionalized with the terpyridine? Yes, you can, because you're going to make a what do you call coordinate bond with these metals, and that coordinate bond can be broken by applying some amount of potential or a current, right? You give certain amount of current. All you need to know is what is that. For example, if it is a carbon-carbon bond, we know how much kilocalorie the bond strength is. So if you give an energy that is above the bond strength, the bond is going to break, right? Same way, you apply some amount of current and break this particular bond, the bond between nitrogen and your metal, and that particular material, or what we call it as a catalyst, will get regenerated. So you can reuse for cleaning the water for that purposes, right? So that is an advantage of the material that we've been proposing to what is available in the market. We can reuse them. And the next problem with the water is we have recently COVID, right? 2 years back, 2020, the whole world is shut down because of the COVID. And the first thing every government and every nation advised is please wear a mask. So now think of what is those blue color masks that we use. They all are polymeric material, right? They are not a woven cloth. They are not a what do you call this, thread or cotton material, right? They are some kind of polymeric material. So we use those blue color mask and of course throw it out, right? Excuse me. And if you look at that, that slowly get into what is called water or a ground, and then finally leaches back to all these rivers and oceans. So if you go and look at these areas, the countries that has been mostly affected, they all started using a lot of mask, right? So the AMU is nothing but of annual mask usage. So the country which is where there is a lot of infection rate, which means that they would have used a lot of mask, which has been discarded, right? There are countries which discard it properly, meaning they'll dig up the ground and then they bury the whole thing. Okay, that is the one way to do it. The other one is some people will burn it, and then the rest is, of course, they've been thrown here and there, and that started getting into the soil. Finally, through soil, it reaches to the water, because it rain, once the rain comes in, it all takes away, right? Whatever the material is there on the soil, it all get washed up. It reaches the local river, pond, or ocean, whatever it is. So in whole process, we contaminated the water bodies. Okay, so that means there are a lot of plastics that is also entered into the water. Normally, when we talk about water, people will be worried about, like as we said, the heavy metals and pathogens. But now we have, with the industrialization and with advancement in technology, we have another problems of plastic entering into the water body. So there should be a mechanism by which we should be able to clean this plastic. So these are called what is called microplastic, meaning they're few micron in size, up to 5 to 100 microns. You can keep it up, right? Even 5 millimeter also get into that. So you will see a lot of plastics that has been accumulated. If it goes into the sea, the what do you call, fish will start eating them or start consuming them, and then finally those fishes will reach our home, and then we start eating meat, right? And that is the way all these plastics enter into our body. Is it really harmful? Is that problem only in different parts of India or all around the world? If you ask me, it is all around the world, and that is why we have called what is called Mission Ganga, was being created by our Prime Minister, right? Where we wanted to clean Ganga, free from everything, free from pathogens, free from heavy sewage mixage, and free from whatever the natural calamity or man-made calamity that can be done on the water. So in that, we wanted to look at how much of microplastics are there. And if you look at it, there are 3 billions of microplastics that gets into the Bay of Bengal, right? And if you look at this particular figure, you can see the map of India is very, very bad. India and China, their water bodies in those countries are actually populated with a lot of plastics, right? Excuse me. Yeah. So we need to clean these. How do we do that? So of course, again, another problem also, I will talk about it almost at the end of my talk, how the plastics that has been used as a water bottle, that plastic from the water bottle enter into our digestion system. I have that slides also. The material that what we call it as a bisphenol. So we just give an introduction to that. So this is one type of water contamination. Basically, the plastics from around us or whatever we throw will contaminate the water body. So in addition to cleaning the heavy metals and in addition to cleaning the pathogens, we also now think about or worry about how to clean this plastics. Will RO be sufficient for this? Sometime yes, some answer would be probably no, because RO is a system where you can clean off, remove the minute particle or smaller in size. It works based on the size variations, right? So most probably it should give us solutions, but then you need electricity. The process is very expensive, and those are the places where you can think of using the carbon that has been functionalized with what we've been talking about, right? Different types of chemical. You can use EDTA, you can use any of those chemical that functionalize it. We took as one example for a terpentine, right? So the water, basically the what do you call plastics, is it entering into the human blood? There are a lot of research has been done recently. This paper has been published a year back, and if you look at it, they actually figured out it enters into our blood system, and they also calculated all this basically using GCMS. And then if you look at all this PET bottle, PE, so that is what has been there. You can see these kind of plastics in our blood. Polystyrene, polyethylene terephthalate, that is what we call it as a PET bottle, right? And I'll talk about that also towards the end of my talk. So now the biggest question is, do we need to invest so much money in generating plastic? So that is the next question we ourselves can ask. Sir, do we have to use so much of plastics? Is that company cannot ban the production of plastic? So that again, the government has to make a decision and people has to follow around, because with the advancement in technology, with the industrialization, we also get used to using plastics right from the day we get up till we go to the bed. Everything that we use is a plastic. I'll give you example. You brush, right? The toothbrush, it's made of plastics, and then we go to the bed, and that bed these days also made of plastics, right? Earlier, people used to make with a natural material like a coir and different things. Now we use a rubber material, and there are some plastic that has been added to give us strength to these. So those are the problem that we need to address, and then also have to think about, do we have to really invest so much money in this, which will be used only for few minutes or few hours? That is what is a question will be. So how do we remove this? As we said, you can make a gravity filter. It's one example of almost like a gravity filter with a little bit of pressure from our tap water, and then the water which you get would be pure from it. Or you can use an RO system and things like that, right? Also, you can apply electrochemical technique. When you do this electrochemical technique, you are going to generate what is called hydroxy radical. These hydroxy radical will go and slowly attack the microplastic and convert them into smaller material. So basically, from a polymer, you get into the monomer. How do you make a polymer? Starting from a monomer, you polymerize it, you get a polymer. And once you generate these hydroxy radical, the hydroxy radical will slowly start degrading these plastics and then get into the monomer. But this process takes a little longer, So that is a question. The electrode are used will be more expensive. They are not made of iron or a steel, or then which degrades over a time. If you need to use in a bulk scale, you have to think of using them as an iron or a steel electrode. But then even they are susceptible for corrosions, right? So we need to come up with some electrode that has been used for a long process. One advantage of this one is you can use it for several years, and there are a lot of different techniques you can use as organosilane as an agglomeration. So basically the organosilane will go and complex with all the plastics, and that can be removed easily, right? As like a bigger precipitate. If you need to think about a reaction, organic reaction, you get a product in a form of let's say gaseous state in a liquid state, and there is something that comes as a precipitate. The precipitate, you just filter it and then throw the precipitate, right? So something like that, you can make a gel, and that can be easily removed. And this is one example where that particular author has done some work. I just wanted to highlight it. So now let's get back to actually our work, right? So is that okay so far? Hopefully I'm audible also, right?
Yes, sir. Yes, sir.
Yeah, there isn't any break. Okay, good. So Yeah. So what our title of the talk is different forms of the carbon or the functionalized carbon, how that can be used for, let's say, sensing applications. Because I do not personally work on energy related area, though we do small work in terms of doing oxygen reduction reaction or hydrogen evolution reaction and all. We create a catalyst for those, but actually the fuel cells and all those things are built by the different groups in our laboratory, right? And one group where the person involved would be our Dr. Satish, who will deliver a lecture on afternoon. So if you have any doubt in terms of either a battery or fuel cells, please feel free to ask him. And he's specifically going to talk about maybe on this particular place supercapacitor. That's what I assume. He's expert in a supercapacitor in terms of synthesizing and everything, right? So coming to our talk, we have different types of carbon, right? So we're starting from graphite. Graphite is the one that we see on our pencil head, right? So that is a graphite that we know. And then diamond also many of us know, right? Because it's very expensive and all the ladies in the house, they like the diamond, right? So that is another expensive form. But if you really think about it, all these are different forms of or allotropic forms of carbon. And we have what is called fullerene, and now we have carbon nanotubes, and then graphene. It's very interesting to know how this particular chemistry is being folded. Normally you start with a sheet, fold them, make a tube, and then you fold them, make a ball. But then the nature is given in such a way that we first understood the ball kind of thing, what is called Buckminster fullerene, right? That is what we know in the earlier days, and the Nobel Prize has been given for that particular invention. And then slowly people invented what is called this carbon nanotubes, whether it be a single wall carbon nanotubes or multi-wall carbon nanotubes. So from ball, we moved slowly into the nano tubes. From the tube, then we open into what is called the sheets, graphene, and that is what I showed 2 slides before also, right? So you can, and graphene also got a Nobel Prize for this particular discovery, right? And same thing with the carbon nanotubes also. So you can understand the importance of carbon chemistry, because the whole area organic chemistry comes in where we deal with normally carbon, nitrogen, sulfur, and especially with a lot of carbons, right? The nitrogen and sulfur, you can just say that it's like added or a dopant kind of material, like a pyridine structures or thiophene structures, right? Or oxygen that can be furan structure. That is what we talk about. But they all will have a carbon as a backbone. So that particular chemistry is very, very rich. So can we use this carbon to make what is called a biosensor? Okay, that's basically our idea. Okay, and there are different forms of the electrode that we can use, right? If you know a little bit of electrochemistry, whatever, probably I'll talk about it, will make more sense. If not, probably we can have a discussion after this talk. Someone can send an email or forward your email to the ma'am, Krishnaveni ma'am, and she will get back to you guys, right? So we have what is called working electrode, we have a reference electrode, we have counter electrode. That all we worry about is because each one is used for a different purposes, right? Reference electrode name itself says a reference electrode, so that has been used as a reference point. Counter electrode is also where we wanted the potentials can be varied with respect to both reference as well as a counter electrode, right? So that is the working electrode is the one where we do a lot of chemistries, whether it be a battery, whether it be a fuel cells or supercapacitor or sensor. We wanted to modify these working electrode, and what are the material that can be used as a, for example, working electrode? You can use a noble metal, right? You can use a gold, you can use a silver, and you can use a platinum. All these things can be used, and also in addition to the noble metal, we can also use a cheaper material, which is carbon based material. When you come into the carbon electrode, there are different forms of carbon. Graphitic rod, and it can be in a plate form, disc form, and the one which we all the time we use in our institute is what is called glassy carbon electrode. It is something like your graphene only. sp2 hybridized carbon would be there, and it will be very shiny surface, and they are not as expensive as either say gold electrode or platinum electrode. Now you know what is the gold price going around in India, right? It's just shooting up every day. It's just shooting up. So the other forms of electrode is you can use an array which can be printed. So polymer imprinted arrays can be used, and cloth can be used, and sheets. And there are different forms of it right there. And if you go into that catalytic industries, people will started using a foam and felt, right? So there are different forms of electrode. Very specifically, I am going to talk about what is called this glassy carbon electrode. How do we take a glassy carbon electrode and modify with what is called carbon nanotubes or graphene based material? Why do we need to modify these, right? So that would be your next question. Right. So we have DNA molecule, we have antibodies. These can go and interact with your disease-causing bacteria or pathogens. Right. The reason why we move from carbon that is being functionalized with a nanomaterial or carbon that is being functionalized different types of material like a dendrimer antibodies, or the size of the pathogen that we talk will be very close to the size of dendrimer, very close to antibodies and things like that. So we need to take a carbon electrode and functionalize with whatever the material we want. For example, in this case, let's say I'm going to functionalize with graphene, and that graphene has to be added or linked to what is called antibody so that it goes and bind with the antigens, right? If you have been infected with any bacteria, first thing that gets generated in our body is an antigens, meaning the disease causing bacteria will start propagate and antigens get generated. Once that antigen gets generated, our body recognizes someone else is coming into my house, so I need to protect my house. So if the body start reacting, and then it generates antibody, this antibody goes and binds with antigen, and then we will be cured of the disease. So when the COVID comes, because the antigen from the COVID is new, right? Is it contain RNA or DNA? From the COVID. Anyone knows? I think probably, I guess probably it is muted for all. So it's okay. Yes. So
but they can send message in chat boxes.
Chat boxes. Okay. Okay. Good. Okay.
Yes,
so no.
You can also access, but we have received Dr. Shilpa BS RNA.
Yes, correct. So right. So it's an RNA molecule. So what then RNA has to slowly induce our system body to generate antibodies. Since it takes a lot of time, because our body, everyone's body will react differently, meaning it takes a lot of time for our system to respond, and that is why people have been infected, and then a lot of unfortunate incidents have taken place all around us, right? So that is why now they come up with what is called these vaccines. If you really think about, there are two types of vaccine. We don't get into that too much detail, but if you think of polio as a just example, they give a dead polio virus, meaning they are training our body with a dead polio virus. So even if it takes a longer time to generate antibodies, when actually the polio virus senses, our system will react faster. It's like giving a training to that. If there is an IPL match is going on, so they practice on the net. It's something like that. You give a dead polio virus, so our body takes a time to generate antibodies. By that time, since it's a dead polio vaccine virus, it's not going to do anything, right? And then our body now knows how such viruses enter our system, how it should react. Then it generates antibody quite faster. And same reason why this vaccine for COVID is also given. So now let's say, how do we take these understanding and then make an electrode to detect some of the bioanalyte? I think even the last talk also I talked about dopamine being a sensor. So normally in the lab, any student comes in, first we train them on a neurotransmitters, because the dopamine is one of the neurotransmitters, and we have mood swing, right? Sometimes you feel very happy, sometimes you feel very sad, sometimes you're tensed, sometimes you're very relaxed. On all these depends on what kind of chemical that has been secreted in our body, so that also play a crucial role. So we need to understand what is being produced and what is the concentration of those chemical to understand whether we are healthy or not. So such few analytes are something like a dopamine, ascorbic acid, uric acids, tyrosines, phenylalanine. These are some of the bioanalyte that can be analyzed to find out whether we will be infected with, let's say, for example, Parkinson disease, or for example, gout. Gout is nothing but like inflammation in your legs and all, right? If you have too much of salt uric acid, or if you have too much of tyrosine, then we will be exposed to the body, I mean, the joint pains. People with the diabetic and blood pressure, they will always complain about it, right? That they have a joint pain and all. So we need to see how these analytes can be analyzed using such material. So again, the carbon-based material can find application starting from supercapacitor, fuel cells, solar cells, hydrogen storage, sensors, absorbent, and catalyst. We'll talk a little bit on sensors and catalyst, and some of the other topics will be covered by Dr. Satish. Not all, but few of them will be covered by Dr. Satish, right? Who is expertise in other areas. So the graphene, as I already talked about it, it's basically sp2 hybridized carbon, and the bond length is 0.142, and it is very, very advantageous because they have high electrical conductivity, right? And then if you look at it, something like a single wall carbon nanotube and multi-wall carbon nanotube, you can have a single layer of graphene or multi-layers of graphene, right? And the stacking distance, if it's a multi-layer, it's something like 0.133 nanometers. Okay. So these are some of the properties of the graphene-based material. And again, as I said, the Nobel Prize has been awarded for that particular invention, right? Normally, the graphene is synthesized in two different ways, right? One is called top-down, the other one is called bottom-up. In a top-down, you start from a graphite. Let's not worry about what is you see on the slide. I'll just give you a simplest example. So you take a graphite, you put a scotch tape. For example, even a pencil is okay. If you take the lead from a pencil, you put a scotch tape on the lead, right? And then remove the scotch tape. You will see small black precipitate or a black particle that is sticking to the tape, right? And those are called actually single layer of graphene. So if you take a scotch tape, put it on a graphitic lead, and then remove the scotch tape, whatever you see on the scotch tape, the black form, those are called graphene. Actually, they will be single layers of graphene. So can I take this graphene and do my sensing process? Probably not, right? Because it's on a scotch tape. And how do you slowly scrap these graphene, and then how do we use this as a sensor? It will be a problem. So chemically, how we can do is you take this graphene, oxidize using highly oxidizing agent, then we get what is called graphene oxide. And that once you get this graphene oxide, then you can reduce them back to graphene, right? You use a strong reducing agents like sodium borohydrate, hydrazine. These are some of the reducing agents that as a chemistry faculty or a chemistry students we know, or as a research scholars you all know. So you can use any of these reducing agents, convert these graphene oxide into graphene. So, so starting from a graphite, you can get into the graphene oxide and then graphene, enough for a multi-scale purpose or a bigger scale purpose. The scotch tape will be very useful if you want to make a very, very small areas of graphene, right? That is can also be done. And only problem with this, as I talked about it, is in terms of the graphene has got wide applicability in wide areas of science, right? We have seen from batteries to sensing, it can be used in many places, but then the synthesis of this graphene is still a challenge. You cannot use a scotch tape for a scale-up process. Even when you do the chemical synthesis, we don't get as much pure graphene as we get on a scotch tape, right? Because you are doing everything on a chemically, and there is always going to be defect in that, and there is always going to be contamination in that, right? It's something like you take a semiconductor, if you create a hole, it's going to be a p-type semiconductor. If you create excess of electron, it's going to be n-type semiconductor. The same thing is going to happen when you do this graphene scaling up. So you can just see that if you look at the scalability versus the cost, you can see if you use a scotch tape, this cost is going to be very, I mean, you get a high graphene quality, but if you need to do it in a larger scale, this cost is going to be very, very high, and also it's going to be time consuming. But if you take a thin graphite and do this chemical, the scalability will also be less, the cost is also be less, but then the graphene quality is actually on the bottom, right? So we need to find somewhere like a compensation, which material can be used or what type of graphene can be used for what purposes. That is what, based on the application, we can define what we wanted to produce it, right? So this is a schematic of Ammer method. Let's not worry about it. You take a graphite and then put a lot of oxidizing agents like H2SO4, KMNO4 and all those things, you get a very black color which is called graphene oxide, and then you add what is called diamine, right, or hydrazine, for example, or sodium borate, these kind of strong reducing agents, and then you can get a graphite. And also we need this famous method is called Hammer method that need to be modified because the chemical I've been talking about is sulfuric acid, KMNO4. These are highly oxidizing agent. At the same time, they are also going to cause environmental hazards. They are not environmental friendly chemicals. So then people need to work on modifying the method we make graphene oxide, right? It can start from a graphite or it can start from a different material. Let's look at some of these, right? And that's one thing. And the next thing is, if you take a pristine graphene, this is your band gap, right? The center one is called a pristine graphene. If you take a p dope, of course it's whole. If you take a n dope, there's going to be excess of electron, right? So you can dope, for example, nitrogen, make it excess, and then you can just see that how the band gap varies if you do these kind of doping, right? So starting from 1.93, which is your homo-lumo, right? This is a homo, this is a lumo. And the band gap is 2.8 and 2.81, 2.71. The band gap is not going to be big different, but the levels of HOMO and LUMOs are changing. Also, the levels of Fermi levels is also changing drastically, right? And that's going to play a lot role when you do this or develop a sensor. So you can develop a sensor for oxygen ORR reduction, oxygen reduction reactions. You can also develop, like, for example, catalyst for HER using these kind of graphene, right? So we'll talk about using graphene as such and also introducing what is called nitrogen and phosphorus into the graphene, and that how that can be used for sensing purposes also, right? So coming back to the people, I mean, I already gave a talk where I talked about a little bit on electrochemical sensors. Now we touched upon two areas. One is water, the other one is especially carbon-based material. We talked about a graphene-based system, right? So can we use this graphene for a biosensor? If you have to introduce a biosensor for the people who are new to this area, I'll just give few examples, right? Or I'll just give an introductory remark on a biosensors. Basically, biosensors is nothing but you need to convert biological response into electrical signal, and that can be measured using a, let's say, handheld systems or a computer, things like that. One of the best example of electrochemical biosensors, which many of us know, almost all of us know, is a diabetic meter, right? So the diabetic meter, we know how it works. You basically have you prick the small blood and then you put a small strip, basically using a, capillary actions, the blood enter into the strip, and then you take the strip, insert into the machine, you get some reading which says this is your blood per milliliter or something like that, right? So that is the reading that we get. So that is the best example of a biosensor. The reason being is that the strip that we use is contain an enzyme, right? And that enzyme is called glucose oxidase. So what it does is it specifically goes and looks for sugar molecule or glucose molecule in our blood, convert that sugar molecule or oxidizes those sugar molecule into gluconic acid. So during this process, a number of electron comes out, and that has been converted into a signal. So the system has been calibrated for known quantities of sugar molecule, how many electron will come out, and what would be the signal, and so that you can work with the unknown system. So that's a best example of one biosensor. So what are the components that are involved in a biosensor is basically a bioreceptor. For example, in this case, the bioreceptor is a glucose oxidase, right? The glucose oxidase is a one which recognizes glucose molecule. It won't go and interact with anything else in the blood. In the blood, we have protein, we have so many other analytes that we already talked about. If you want to really analyze, let's say, tyrosine, that is also there. If you want to analyze uric acid, all these are part of blood, and that is why when we give a blood sample is in a laboratory, they give a lot of profile, right? They give what is called diabetic profile. They give what is called salt profile. They talk about sodium, chlorine and all, because those are used as an electrolyte in our body also. That is why we are actually moving around, right? Is it so far okay, or is it fine? We all are doing okay?
Yes, sir. Fine, sir.
Okay. And the next one is an interface, right? And the third component would be transducer element, meaning whatever the recognition has been taken place. Now the glucose oxidase will go and find glucose, convert that into gluconic acid, electrons is being produced. That electron has to be fed down to a reading system, right? So that's where the transducer plays in. And of course, we have a computer software and user interface. So that will be very easy from this particular system, right? So this is where we are going to play around. This is an electrode. For example, the glucose strip is what I've been talking about. The strip is now, in that particular case, has been functionalized with glucose oxidase. In this case, we are going to functionalize with carbon-based nanoparticle, whether it be a graphene or whether it be just a carbon dots. You can use any of those, and that will be again functionalized with some recognition element, right? So we'll talk about those recognition element. And once we have this recognition element, that will be very specific to that particular molecule. For example, let's say I want to find out an ascorbic acid. Ascorbic acid, as a name suggests, it's going to be COO minus, right? So if I have a positive charge on the carbon surface, there could be electrostatic interaction between these two. So I can selectively detect ascorbic acid instead of dopamine. If you think of dopamine, it's got NH2, right? And in acidic condition, it's going to look like NH3 plus, right? So that I can remove this positive charge with a positively charged my surface, and I can very specifically detect ascorbic acid. Uric acid will also play, so we need to be very specific or tune our system so that it detects only ascorbic acid, not a uric acid. So we'll talk about it as we go along, right? And there are different techniques that can be used when you want to sense a system, right? You can use what is called amperometric sensing, you can use a potentiometric sensing, and also we can use what is called impedance. Impedance is nothing but resistance, right? Amperometric is you're going to apply a constant potential between a working electrode and a reference electrode. Normally we work with the 3 electrode systems. That is what I talked about in the beginning of the talk. We work with working electrode, reference electrode, and a counter electrode. If anyone interested, what is the role of this and how this is advantageous compared to the 2 electrode system, we can talk about it, right? No problem. So you have a constant potential that has been maintained between the electrode, working electrode, and a reference electrode, and whatever the current flows through this will be recorded, right? In a potentiometric sensor, the potential is between a working electrode and reference electrode will be is being measured, whereas the current is being kept constant, right? So that is a difference. And impedance is where we want to measure the resistance, and those are used for if you want to figure out what is the concentration of irons in our body. We can use impedance kind of technique, right? So if you go to the lab, you give a blood samples, and then they give you all these values, right? And those are used on, let's say, spectroscopic technique. Normally, those laboratory techniques are used using a what is called absorption spectroscopy. They'll be looking, they'll add a certain chemical, induce color to that system, and based on the absorption value, they'll tell you what is the levels of, let's say, your sugar level, what is the levels of your triglyceride level, what is the levels of sodium, or what is the levels of potassium, chlorine, and in electrochemistry, we are also going to look at it, but not in terms of absorption, but in terms of current value, or in terms of potential value, or in terms of resistance. That is what we talked about in the last slide also. So these are different techniques, and we talked one example being used glucose, and the same thing can also be used for lactate sensing also. So there are people, even in our country, it is very common in abroad, people will be resistant to lactose, meaning if they drink milk, the body will react to that. People milk intolerance, they cannot take a milk at all. So the body will start reacting. They will have a lot of other issues when they consume milk, right? And that is called glucose intolerance, right? And if the levels of, similarly, like the levels of sugar molecule, the levels of lactate is also important, right? And that also gives you an idea about what kind of disease will be exposed in the coming days or in a coming month. So by monitoring some of the chemical that is being generated in our body, we can tell whether we are going to be healthy in the coming days, or I may susceptible to some of the disease. If we figured out that we be going to be susceptible to certain disease, we can take a remedial action. That's the advantage of all these electrochemical sensors. The next question you can ask is, why do we want to go for an electrochemical sensor compared to what is a technique which is already there? Now you give a blood sample, right? At least they take minimum 2 hours, and for certain experiments they take 1 or 2 days, right? During this COVID period, they have to do what is called RT-PCR, right? It's a polymerase trans. So that particular technique, it takes 2 days. Depending on the load, it takes either a day or two, but minimum it takes a day, because they need to do what is called this chain polymerase reaction, and then I have to tell you how much you've been exposed to that. Whereas if you use electrochemical sensor, the results will be very instantaneous. And also you don't need a complicated instruments like UV absorption, or even for RT-PCR, there's a big instrument, right? We don't need such kind of big instruments. You can do something very handy, that as you can see, the diabetic meter, that's the size of the system that we've been looking on. And that is why these electrochemical sensors are very attractive these days, right? Glucose, now let's say, how we all are sensing is sensing through the blood. Is there any other alternate? We'll think about that alternate also. If anyone knows it, please do it in a chat box also, so that ma'am can tell me, is there any answer from the students or faculty side? Right now we are sensing glucose using only blood. Can we sense glucose in our body using a different starting material instead of blood? Can we use something alternative? That is an alternate. Please suggest me what are those alternate, and I'll also touch upon that as we go along. Right, lactate sensing, as we talked about it, is very, very important for athlete, because the excess of lactate can take into what is called respiratory failure. That is why when you run, or when you exercise, or when you play for a longer time, people will normally go for a lactate test just to make sure that you are okay. If you're not okay, then you get admitted and then you give a drips and all, right? So that is so sepsis and tissues hypoxia will all happen when there is in levels, either a low or high levels of lactate is there. Again, you can use an enzyme called lactate or lactate oxidase. It specifically transfers lactate into pyruvate, and during that particular process, again, you produce hydrogen peroxide and electron that can be recognized using our system, right? So similar to diabetic machines, you can actually generate what is called lactate. Is it still commercially available? Not as popular as a diabetic machine, because they are very specific. Normally, these are used by athletes, right? And even these places, we can take a graphene oxide or a carbon nanotube, functionalize them with the gold nanoparticle, and which the gold nanoparticle will be again functional with certain types of either enzyme or semiconductor metal oxide material that will convert your lactate into pyruvate. The idea is, if you use an enzyme, it is very expensive. Also, they will have what is called expiry date or a shelf life period, right? That is why when you go and buy this glucose strip, they will tell you this has to be used in 6 months time. This need to be stored in a refrigerator. And the reason why they say is because that strip contains an enzyme. That enzyme will lose its activity, or the enzyme will get denatured if it is not being stored as instructed, or if it's not been used within that particular period of time. So how do we avoid it? We can avoid using enzyme mimic metal oxide. We can avoid using enzyme mimic material, and normally we use a metal oxide as an enzyme mimic material. We'll talk about it also. So whatever the lactate oxidase will do, for example, manganese oxide, MnO2, right? I can make a manganese oxide nanoparticle, functionalize my graphene or a carbon with these manganese oxide nanoparticle. That manganese oxide nanoparticle will specifically oxidize only a lactate to pyruvate. Then I say that that's an enzyme mimic of my nanomaterial, enzyme mimic nanomaterial. Right? So there are some cardiac bio sensors. That is what we talked about, right? Normally people will take about N-terminal BNP. If we need more detail, we can always talk about it. And I don't know how many of you remember, during this COVID period, people who do not have access to RT-PCR, in the later point of time, the doctor used to tell, please go and find out how much is CRP, right? And that cost literally 40 rupees, whereas your RT-PCR would have costed, if you're doing it privately, it would have costed 1,000 rupees. If you use through the government sources, it could vary from 200 to 800 rupees, right? Whereas on your C-reactive protein, it would have just costed 40 to 60 rupees only. What it tells is, there is an inflammation in our body. The C-reactive protein level, the acceptor levels is, I think, 1 or little less than a 1. If you have anything above values of 1 microgram per milliliter, which means that you are exposed to certain inflammation. It could be just a running nose, it could be a arthritic pain or anything, but it won't tell you what disease it is. But you just say that the body is being inflamed due to some unacceptable material that enter into our system. Then you can actually do the analysis whether it is due to this bacteria, whether it is due to other viruses, and all those analysis can be done. But the simplest technique is to find out what is the concentration of C-reactive protein, and that is can also be useful for finding out whether we've been affected with the cardiac thing. And then this tryptophan is another biomarker that has also been used to figure out whether the levels of tryptophan will give us an idea what is good, whether our system is working fine, or I'm doing okay, or will I have an heart attack in some point of time. Normally, we always say, right, there will be a sudden heart attack. As far as my understanding, I'm not putting anybody. My understanding is that it is never happened all of the sudden, right? It gives you a lot of indications that only that particular individual will ignore all those indicators, and that is why when they get an heart attack, they call it as a massive heart attack, and then it happened all of a sudden. Normally, it never happened all of a sudden. Before we get one person get a heart attack, there are a lot of chemical that is secreted. It could take from week to month, and all these you may feel very tired when you do exercise, right? When you take up a stairs, you may feel very tired, meaning indicating that you've been having some problem. Only thing is we ignore those symptoms, and that is where leads into what is called massive heart attack. And one way to confirm whether that symptom is related to heart attack or not is that you find out the levels of these analytes. Once the levels are within acceptable level, then they are just a normal. You can just take precautionary measure. If the levels are very border, then you really have to start taking a medications. That is what it is, right? There are different types of probe that can be made, and you can take a screen printed electrode, and then you can look at what is called this amperometric sensors for CRP as well as NT-probe BNP, right? Let's not worry about all this. The idea is you take graphene based material for these, and these are some of the literature material that I've been presenting. Now we'll talk about some of our material that we've been using for it, right? And now when you do this kind of sensing, you have to take a blood sample, right? Once you take a blood sample, the question would be, do we really require a blood, or can I try something else? Because when you prick it, it is painful. A person with a diabetic, for example, my mother is a diabetic, every alternate days or once in a week at least, she checks her sugar level. Every time she has to prick, which is very painful. And there are non-invasive techniques that are slowly coming up, right? So instead of taking a blood, we can take, I asked that question also, right? Instead of taking a blood, we can take a saliva, we can take a tears, or we can also do epidermal senses, or also use a sweat as a material from which we can do all the analyte concentrations, right? So moving from now, let's say lab based technique, we moved into what is called home based remedial system. That is, from a lab based blood samples, we moved into what is called generating a diabetic meter, and you yourself can tell us what would be your sugar level. Now from that, we are still moving into very advanced levels where we do all these wearable biochemical sensors, right? One of the best examples that these days we know is smart watches. The smart watches are wearable watches. It tells you so much of health parameters, right? Each one works on a different mechanism. For example, you press level, right? How it works is basically it transmits a light. Once you press that, you know there will be a red or a green color light will pass through your skin. You can just see the light, and then how much time it takes to reach your nerve system and then come back to that is being measured. Based on that, they will tell you whether your blood sugar level or heart bumping is normal or not. Something kind of techniques are possible. So the wearable sensors, you can think of so many wearable sensors. To do the wearable sensors, we need to make a material that is also flexible in nature, right? So, and that is why we can move from let's say your standard costlier material of gold, silver to very cheaper materials of carbon, because you can use those as an electrode material and embed them into the wearable sensors. For example, you can use eyeglasses using which you can find out a lactate and glucose levels. You can use a smart contact lens. Using that particular lens, if you have a, let's say, a Bluetooth connected smart phone, it tells you how much is your sugar level. These are all continuous monitoring that can be possible. If you use a mouth guard, you can tell how much of uric acid is there. If you have stones problem and all, there are uric acid in the urine is very high, so that gives an indications that we are going to have a kidney stone in the coming days and all. And there are a lot of microfluidic sensors, sweat sensors, right? And also you can use integrated sensors. Mostly they talk about sugar, lactate, and some of those amino acids that I've been talking about, and uric acid that we talked about it, right? Let's not worry about all this. So the idea is, again, we wanted to make these flexible sensors. So we need to convert all these polymeric substrate, polyethylene, phthalate, polyimide, into what is called conductive medium. Once you have a conductive medium only, you can, so we can move slowly from a carbon based electrode to all these plastic, where you can embed this carbon, and that is what MIP, it's called imprinted polymer, right? Micro array imprinted polymers, and then we can use those as a sensors to detect some of those analytes. The best example would be a smartwatch, which can tells you in a coming days probably all the electrolyte level, the levels of glucose, uric acid, lactate, ascorbic acid, urea. All these will be figured out now in your fingertips, meaning in your hand itself. Those are we are not far from that particular time. You can take a skin, and then the fluid, you can take it and you put a sensors, and there are a lot of electronics on top of it. So this is the simplest examples of how these wearable sensors work and what are the components that are there in the wearable sensors, right? Blood alternate, already we talked about it. You can start from contact lens, tear sensors, sweat sensors, all those things can be used. And also one of the things which I have not told in the previous slide is you can use interstitial fluid also, and then sense basically sweat and all, right? It comes out of the skin, and then you can tell how much of these bioanalytes are there in your sweat, things like that. We'll go back to some of our work. I'll skip some of these. I don't know how much time I have, ma'am. Hello, do I have another 15 minutes or half an hour?
Yes, sir. Yes, sir. Yeah.
Okay.
Yeah, please.
So basically, now we'll talk about it. I said when you do this, these are some of the work that I wanted to present. And how we, yeah. Yeah, these are some of our work, and then I just wanted to show how we generated few sensors using naturally friendly techniques, right? So I said when you want to make a graphene, you have to synthesize from graphene oxide, use strong oxidizing agent, and then convert them or reduce them using again strong reducing agents, right? Instead of that, one of our students has made a small approach where he took a carrot extract, and then that graphene oxide, instead of using a reducing agents like hydrazines or sodium borohydrate, lithium aluminum hydrate, which are strong reducing agents, but also they are not environmental friendly, right? So we took carrot extract. That carrot extract got, everyone knows, beta carotene, right? And they also have lycopene, lutein, and then epileptin. There are different chemicals are there in the carrot extract that act as a reducing agent. So we started from a graphene oxide, reduced them into graphene using a carrot extract, right? So can we use this graphene for sensing purpose? If we need to use this graphene for a sensing purpose, first thing is they need to be characterized and make sure they are reduced into graphene. Normally, not all of these graphene oxide will be reduced to perfect graphene. That is what I talked about it. If you take a graphite, put a scotch tape, and then take it out, what you get is a perfect graphene. But whenever you do the chemical synthesis, normally they will have a defect. So we are going to use the term what is called reduced graphene oxide. It's not a graphene, we call it as a reduced graphene oxide, which is very closer to the graphene, right? So we need to do different types of analysis. Once you know it gives you a Raman spectra as well as they are active in FTIR spectra, right? The graphene material is active in FTIR as well as in Raman spectrum. If you look at the bands in a Raman, normally people will be worried about D and G band. D band is due to defect areas, and then G band is due to sp2 hybridization, right? So if the ratio is very close to 1, you say that the graphene is a monolayer and it's a perfect graphene. If 2D by G value is closer to 2, then you just say it's a single layer of graphene, right? So we do not worry about it. So we took this carrot extract, reduced this graphene oxide into what is called reduced graphene oxide. We subjected that particular material into different technique like FTIR technique as well as X-ray technique, and you can just see that they are very matched. The values are very close to pure graphene. And when you do the absorption, you can also see that pi to pi star transitions occur at 230 nanometer. There is a shoulder peak which corresponds to n to pi star. So if there is a multi-layers of graphene, then you know there is a pi to pi star electron transfer can take place and n to pi star can take place. Or if you are organic chemist, then you all know the sigma to sigma star is not possible because the energy band is very, very high, right? It's something like an insulator. And whereas if you have pi stacking, benzene, naphthalene, anthracene and all, you know, n to pi star, if you have lone pair of electron, it can go from n to pi star or from pi to pi star, right? Those things are possible. Those things are quite possible with that. So we characterized our graphene using a different technique, for example, FTIR, UV as well as a Raman spectrum, and confirmed that whatever we reduced using a graphene carrot extract is reduces graphene oxide into what is called reduced graphene oxide. And the higher end, we also use XPS, X-ray photoelectron spectroscopy, right, or also called OJ spectroscopy, and we can characterize them, and you know what is the levels of carbon and oxygen and nitrogen. So if you look at those things, so those are the peaks which you looking at it, right? Carbon, oxygen, and then the ratios of carbon to oxygen. This already we talked about it. If you have pure graphene, what would be the band level? If you dope them with a nitrogen or dope them with a phosphorus based material, what would be the band gap level and how it changes and all. So what one of our student done is, she took glassy carbon electrode, that is a normal electrode we use, right? There are 4 electrode I talked about it. One is gold, silver, platinum, and then glassy carbon. Gold, silver, platinum will be expensive, and you can use a glassy carbon electrode which is very cheaper also, right? So you take a glassy carbon electrode, now try to functionalize them with a different functional group, right? Take a glassy carbon electrode, functionalize them with a graphene and attach functional groups also to that. That is what we can do. One example is we have taken a graphene attached to the glassy carbon electrode. Because of sp2 pi interaction, they will go and nicely stick onto the electrode. Now if I have just a graphene, they are not very useful, right? They cannot go and interact with my biological system. So I need to functionalize them so that it will have N group as OH, or N group as thiol, N group as sulfonic acid, or N group as COH. If I have COH and thiol, I can very specifically bind them with a positively charged analyte, right? Any analyte that is positively charged. For example, if it's a dopamine, I can use a carboxylated graphene or sulfonated graphene, right? Or my interest is on, let's say, uric acid or ascorbic acid, I can take aminated graphene, or to certain extent, I can take a thiolated graphene. It will be very specific to some of those, right? So is this a graphene? So how do we functionalize it? We can do this functionalization also electrochemically, meaning you take graphene molecule, you treat them with this sulfonic acid benzene group with a sulfonic acid and amine group, right? So many of you know the chemical name of it. I'm not specifically saying, so that you can again put them on a chat box. If I have only OH group, then I'm going to call it as a phenol. If it's an amine group on a para position, you tell me what is the name. So you can functionalize the graphene. How do we functionalize? One way is doing electrochemical, the other way is doing chemical, right? Chemical is always, I say, there will be impurity. So we try to use the electrochemical technique, and it is also easier. You take a glassy carbon electrode, attach this graphene, and then dip these electrode into the solution, apply certain potential, right? And once you apply certain potential, they get attached to the system, and that can be again characterized. Okay, so you need to apply a potential of 0.9 and then scan them from 0.1 to almost 1 volt. You get acid functionalized glassy carbon electrode on which there is a graphene, and that graphene is now functionalized the COH group, and also similarly that graphene is also functional with sulfonic acid group. So thus I can use for sensing what is called my dopamine, because I talked about it in the last time. I'm not touching on it, but we took this particular system and then did a lot of calculations, how much of functional groups are there, and can we use these to sense some of these material, and that is what has been highlighted here, right? Again, these are not very important. So looking at this scanning electron microscopy and transmission electron microscopic image, this is one particular image from scanning electron microscopy. You can just see that the nice layered materials of graphene. Graphene is a layered material. You can see the carbon as a graphene, right? Let's not too much worry about this. This is one example where I wanted to show that if you take potassium ferrocyanide, right, hexacyanoferrate, can we sense this using some of these functionalized graphene, for example, OH, COH, SO3H, and where it will be very active. That is what is being given here. So if it is a negative charge, for example, OH, the graphene, so there are three materials that has been compared. One is a glassy carbon, and the next one is a graphene, and the third one is graphene with a OH group, right? And if you look at it, graphene and glassy carbon gives you much pronounced oxidation and reduction potential for hexacyanoferrate to ferroferry system, right? Oxidation and reduction. And if you take this OH group, since this is a negatively charged and this system is also negatively charged, there is not much interaction. So this oxidation and reduction is not pronounced as much as you see on a pure graphene or a graphene that is being functional with hydroxide. And the same is opposite when you take this nitrogen functionalized group or thiol functionalized group. Okay. So now take this glassy carbon electrode. I'll just come to some of the interesting system that we talked about it, right? We talked about little bit on this oxygen reduction reaction and nitrogen evolution reaction, and we talk about sensing one of the important molecule, what is called bisphenol. We talked first with the water system. We'll come back to that water, right? Now, what we are going to do is, like a graphene, you also can take a glassy carbon substrate. Now you don't have to do anything. Into this glassy carbon substrate, functionalize them with a nitrogen doping. For example, now we know how to dope the nitrogen. You take an aminobenzene with the containing thiol molecule. The thiol molecule will go and stick to the surface. Amine will be on the outside, right? Or you can also take a different system and then make this as a nitrogen doped glassy carbon electrode. Can we use that for doing ORR, HER, and also for sensing some of these materials? That is what we are going to talk about it. So you take a glassy carbon electrode, now just induce a nitrogen. So the only way to do is you do the chronoamperometry at 0.9 volt. That is what I talked about, 0.96 volt. You can get nitrogen incorporated glassy carbon electrode. The mechanism is already been shown earlier also. And this is how it really occurs in that particular place, right? You are basically it works based on anodic oxidations, right? You have amine, your radical plus negative charge, that's slowly converted into amine based system. If anyone interested, we can talk about this. And also we have a lot of publication based on this particular work. Okay, so moving from a graphene, right now we have seen two different systems, right? One is graphene and the other one is glassy carbon electrode. Those are two different systems. And we took a glassy carbon electrode in the previous case. They used what is called graphene that has been prepared using a carrot juice. You take a graphene oxide using a carrot juice, we get what is called reduced graphene oxide. we functionalized our electrode with that reduced graphene oxide, and then we did a different sensing, right? And that takes little time and also material. So instead of that, can we use as such this glassy carbon electrode without introducing any graphene material? Can we use this glassy carbon electrode for sensing? People have been using this for a very longer period of time. Only problem is when you want to sense, let's say, for example, ascorbic acid, dopamine, and uric acid, as such with the glassy carbon electrode, the oxidation peaks of all the three moiety will come very close to each other. So you cannot have good resolution, meaning, like for example, let's say you are running a liquid chromatography. Whenever you want to separate certain system, they need to come in a different RF value. That is what we study, right? They need to come in a different. Let's say I have three components. Those three components should come in at different intervals, so I can differentiate. This is a compound 1, this is compound 2, compound 3. If use a glassy carbon electrode as such, that differentiation is not possible. But the moment I introduce a nitrogen into that, I can differentiate peaks that is corresponding to dopamine, that is corresponding to ascorbic acid, that is corresponding to uric acid. Same thing can be used for detecting some of the alcohol molecule. For example, I'm going to talk about bisphenol, catechol, and hydroquinone. These are organic molecule which has similar molecular structure and molecular weight is also same. So if you look at the physical and chemical property, they all will be same. So when you want to do or sense these using electrochemical method, very difficult, because they exhibit similar chemical behavior, right? So whenever I'm going to do the oxidation or I'm going to do the reduction, they are going to occur at the same potential. So I need to do something with my electrode so that I can differentiate them. And that is why we introduce what is called this nitrogen into that. And once the nitrogen has been introduced, I can separate those peaks. So how do I know the nitrogen is incorporated into that? There is a XPS technique, as I told you earlier. We can use them and find out how much of nitrogen is incorporated. If you look at that, then we know the carbon is 51%, nitrogen is 24, oxygen is 24.85. Even in that nitrogen, we talk about different nitrogen, which is called pyridinic nitrogen, pyrrolinic nitrogen, graphitic, and then protonated and all, right? So those nitrogens which are in the glassy carbon electrode will be responsible for sensing a different analyte at different potential, right? That is what our main aim is. The analyte should come at different potential. They should not overlap. Like these three different peaks you see, right? Even the electrochemical response should be three independent peaks. They should not overlap like what you see on a red line. If it is like that, then you cannot say which one is corresponding to what analyte it is. So we took a glassy carbon electrode, functionalized them with the nitrogen. Now we wanted to use them for sensing applications, right? And also for OER and ORR applications. Okay, ORR means oxygen reduction reaction, OER is oxygen evolution reaction, which occur at this place. HER is hydrogen evolutions. Normally, people will be more interested in terms of oxygen reduction because that is the chemistry that is used in fuel cells, right? So if you use this nitrogen incorporated glassy carbon electrode, and the blue line you see, right, that is just a glassy carbon electrode. The yellow line or orange line that you see here is nitrogen incorporated glassy carbon electrode. So at approximately 200 millivolt, you see a defined peak that corresponds to ORR, and that is only observed in case of nitrogen incorporated glassy carbon electrode. And if you just use a glassy carbon electrode, the blue line, there is no oxygen reduction reaction that is occurring, right? Or the peaks are not very pronounced. And once you proceed further, this is a place where the hydrogen evolution starts, right? The blue line. The blue line, it starts approximately, let's say 0.7 millivolts, right? And if you look at this, it starts approximately at 0.5. So we are saving the onset potential of 150 millivolts for a hydrogen evolution reaction, meaning you are doing a little less work, meaning less expenditure for hydrogen evolution and for oxygen reduction also. If you use this nitrogen incorporated glassy carbon, and if you come onto this side, right, you will just see the oxygen evolution reactions. Here also you can see the oxygen evolution reaction. In case of orange line starts occurring at 1.5, whereas in case of just a glassy carbon electrode, it occurs at 2 millivolt or 2.10 millivolt, right? So approximately you are saving 550 millivolt of onset potential if you just incorporate nitrogen into that. The next question would be, sir, can we take this glassy carbon, add graphene and then add nitrogen to that? Yes, we can do that. Will that be better than this? Actually, we have done some experiment. We figured out there's not huge difference, and that is why we also suggesting that nitrogen incorporated glassy carbon electrode itself can do a better job than going for a graphene that has been incorporated as the nitrogen, because the cost is also involved, right? So if you look at the ORR, if anyone interested, we wanted to find out oxygen reduction reaction in all pH. Normally they are done in acid, alkali pH, but we wanted to make sure that the oxygen reduction reaction is occurred from pH 1 to 14. So we tried this nitrogen incorporated glassy carbon electrode and we figured out it behaves differently, but in all cases the onset potential for ORR reaction is drastically reduced if you use a nitrogen incorporated glassy carbon electrode, right? And also the next question we have to ask ourselves is, can we use this electrode for many cycles? Can we use this electrode for producing oxygen or reducing oxygen continuously? That would be the question, right? Yes, you can. So we have tried up to 500 cycles for, let's say, HER, and also we have tried 500 cycle for OER and also 500 cycle for ORR. In all these cases, we figured out the onset potential is not varied, or the open circuit potential is not varied, except this particular case. We'll talk about it separately. The onset potential is not changed drastically. In one case, let's say you start with 2.13 and after 500 cycle you get 2.16, which is very, very acceptable after 500 cycle, which means that the electrode can be used for longer time and they're very, very stable. That is what we get, right? And the next maybe I'll just stop afterwards. We're very close to 12 o'clock, right? Very, very interesting point is, we started out with the water and then we probably end with that. We assume that the water that we consume through the water bottles are actually safe. If you look at the water bottle, the use and throw water bottle, they are made of what is called polyethylene phthalate, right? PET, PET bottles. The one of the component that has been used in manufacturing of PET is what is called bisphenol. So it's a monomer using which people start making polyethylene. It's one monomer, right? Not completely. One monomer. Basically, they add this to give that flexibility to the water bottle. You can twist it, you can fold it, but still it won't break, right? And the molecule that is responsible for that particular behavior is what is called bisphenol. So this is a structure that you look at it. So when you store the water in the use and throw water bottle and expose them to the sunlight and all, or transport, because the water bottle is being abused, right, during transportation, during storage, they are not kept in an ideal condition, meaning they are not refrigerated or they are not kept away from a sunlight. They've been exposed to sunlight, they've been under a lot of pressure during the transport. So what happens during this process is, the bisphenol that is dissolved in these or the monomer that is there in the water bottle, unreacted monomer, will slowly get into the water and then we start consuming that water. So there are complaints that we receive from people of different culture, right? They are not exposed to any of the bad habits. They don't use any of the chemicals or anything. I mean, they don't drink and all, but still there is no family history of cancers and all, but still people complain that they've been having a cancer. That will be the first generation of cancer in that particular family, right? And the reason what we figured out is, it's actually a through different study that has been carried out, right? People who get used to a lot of plastics are getting into or susceptible to this cancer, because they use a carcinogen. One example is a bisphenol. And so that we took this as a challenge. We wanted to find out, let's see how much of water or how much of bisphenol is there in the water bottle. So we took this nitrogen incorporated glassy carbon electrode and we figured out, can we sense this bisphenol very specifically? So when you take a PET bottle, there are a lot of other monomers that can also interfere, right? You will have a what is called this hydroquinone, and we have a catechol, we have bisphenol. They have similar structures if you look at them. except maybe bisphenol has got two benzene ring, but whereas your hydroquinone and catechol is one benzene ring with two OH group, right? So they have a similar structures, and so when you do the oxidation and reduction, they will have almost overlapping of peak. So to avoid it, that is why we use this nitrogen incorporated glassy carbon electrode, and then we run what is called LSV, linear sweep voltammetry. And when we run this LSV, you just see different peak that is responsible for hydroquinone, catechol, and bisphenol. If you just take a glassy carbon, there will be one broad peak. Now we know, so you take a known concentrations of bisphenol and then analyze the area under this particular peak. Once there is a calibration plot is done, then we can find out the concentration in a unknown samples, right? Or basically the sample that has been contaminated with the bisphenol using that calibrated plot. So that has been done. And also this is done in presence of these interferent. If there is a other phenol that has been interfering, still you can figure out how much of bisphenol is there. So even if your water is containing any of these three components, you can very specifically tell how much is there in as a bisphenol, how much is there as a catechol, and how much is there as a hydroquinone. So all these are possible with nitrogen incorporated glassy carbon electrode, and this is the calibration plot that I talked about it, right? So you start with the known concentrations and then do this calibration plot. Once the calibration plot is ready, then if you have unknown concentration, that can be easily figured out. So this particular system or the electrode is very, very sensitive. You can detect 2.3 to 0.885 what do you call? Sorry, basically it's very sensitive. You can detect micromolar concentrations of bisphenol starting from linearity goes from 500 nanomolar to 5 micromolar, and then 5 micromolar to 45 micromolar. So if I have a water molecule that contain above 500 to 5 micromolar, I can still use this particular electrode and then figure it out. If the next question will be, sir, what happens if it's less than 500 nanomolar? Maybe our system may not be very sensitive. So we will be able to detect up to, let's say, 0.5 molar or 0.5 micromoles, right? 0.5 micromole to 5 micromole. In terms of sensitivity, the current value is very, very high. So it is very detectable. I think that's the same thing. If you vary the pH of the water, still they are reasonably, you can figure out there is not too much variation in terms of sensitivity. So this can be used for both industrial water as well as a drinking water. And if there is an organic contaminant like a microplastic, if there is an organic contaminant that originates from these monomers, that can also be figured out using this kind of method, right? Let's not worry about this. So this again, simultaneously we can determine all these molecules. That is what we talked about. The last part of it is, okay, I'll just take 2 minutes and then I'll finish it off, right? Everyone like the bread, and in the northern, especially in Tamil Nadu, we like so much of paratha, right? Everybody eats a paratha. Again, this is actually debatable question. There are people who supports what I'm going to say, and there are people who actually vote against it also. But from the town where I live in a place called Karaikudi. That is where the Central Electrochemical Research Institute is located. We went around and then we purchased paratha. We went around and then purchased bread molecule, and we figured certain chemical in that, and that is what I'm going to talk about it. Okay, so is it true for all the areas, all the locality? I'm not very sure. That need to be analyzed, right? So when we take a bread and when we, let's say normally, at least in southern part, not in a northern side, southern part, only when we are sick we take a bread. If you are very healthy, you take a idli, vada, dosa, things like that. That is what in Tamil Nadu, I think mostly also in Karnataka people will do it. Only when we sick, people will suggest you take bread. But then the bread is made from either a maida or a wheat, right? In all these starting material to the maida, they add a chemical called aloxan, and this aloxan is added very specifically just to give a whiteness to the flour. Maida is very, very white in color, right? Just think about the color of wheat. It is yellow to start with, kind of brownish or yellow. You can brownish. Let's put it in terms of brown or skin tone, right? And from the skin tone, if we grind it, how it can be white, which means that it need to be bleached, right? So that it loses that brownish color and become white in color. So for doing that bleaching process or to make it look like white in color, they add a chemical called alloxan. This particular molecule, what you see here, right? This alloxan is carcinogenic, and also it is induces what is called diabetic in many people. So when we are sick, we consume a bread that is made from maida or a wheat. By consuming that on a regular basis, we may be exposed to diabetic, right? And that is a take-home message I wanted to convey, but that is true in our locality. It may not be true, and also this question is still debatable because people are saying they don't add alloxan to that. But whatever we purchase from the local market, we figured there is an alloxan in those bread or the starting. Even we purchased maida as well as a wheat flour, and we figured out these chemical, the presence of these chemical in that. So how do we try this particular technique is, how do we sense this? That is the next question we wanted to ask, right? So also why I'm saying this is a diabetic is, normally whenever there is a medicine that comes into the market to treat the diabetic, right? There are a lot of medicine that are available, right, other than insulin, right? Insulin is the one which directly start digesting your glucose. The all other chemical that we intake will help us to secrete more insulin, right? And these chemicals have been tested using a rat. They basically induce a diabetic to a rat. How do they induce a diabetic to the rat? To induce a diabetic, they inject this chemical, what is called alloxan. So alloxan has been injected into the rat. Based on the concentrations of the alloxan, the rat will be of different levels of diabetic, right? Diabetic level 1, 2, 3, whatever the stages we call it as. And then the medicine that the pharmaceutical company make it, they give it to the rat and then see how it responds. And once the response is good, then they take it to the clinical studies of doing it with a group of people, or and then it comes into the market. So right, so the first place how it been tested is the rat has been induced with the diabetic. To induce this diabetic into the rat, they give this chemical called alloxan. Obviously when we consume, probably we will also will get exposed to the alloxan. So there are different techniques to sense them. Even electrochemically, if you look at this molecule, it's not going to be active electrochemically, right? There is no conjugations or there is nothing that can conduct electricity, right? If you take either a glassy carbon or nitrogen doped glassy carbon, you take a graphene or you take nitrogen doped graphene, to make it very specific to binding with the alloxan is very difficult. Next thing is, they may not be very reactive, in the sense you may not be able to find oxidation and reduction of it. So to overcome that, what we did is we took phenylenediamine diamine. It's a simple adduct reaction, right? So you form what is called this particular complex alloxane. This alloxane is electrochemically active, so we can detect them using electrochemical technique, right? So we took this glassy carbon electrode that has been functionalized with the nitrogen molecule, and then we detected alloxan in that using different techniques, cyclic voltammogram or differential pulse odometry and all. And this is what we've been talking about. So the concentration of the bread, the alloxan concentration in the blood, we figured is 25.03 micromole. And in terms of the flour that they used to make the bread, it contained approximately 35.5 micromoles of alloxan. And of course, this technique has got certain limitations, right? Because the linear range is from 0 to 600 micromoles. So if you go above 600 micromoles or below 600 micromoles, probably this particular technique may not be useful. Then we need to take the start working on variating our working electrode, meaning this working electrode has been now functionalized with the nitrogen. We need to think of different dopant, or we need to think of different material that can go into smaller linear range. But the idea is just to wanted to show that alloxan can be converted into alloxane, and that alloxane is electrochemically active, and that can be detected using what is called this modified electrode, right? And also this adduct is colored in nature, so you can use a UV technique also and then figure out what is the concentration of alloxan in those. And using this particular technique, we can do a lower limit approximately 2.47 micromoles. That's what. It's very specific. These techniques are very specific, up to 0 to 60 micromoles. Right. So if you have any question, probably I'll be very happy to answer. I will stop with that. I just wanted to show one slide. So we now start moving from all these blood into different invasive technique, right? And that is what we also have to come into the state where we need a self-powered sensors, meaning you put a small tattoo on your hand, that should be able to tell you the levels of, let's say, lactate and a glucose. We already saw that, right? Or you take a mouth guard, it should tell uric acid, but they will have all small battery inside. Only if there is a battery, it works, right? In absence of battery, they don't work. But then you can, now there is going to be a time where you may not need to change the battery, but still these sensors will work. And that is where the self-powered sensors are coming in. And that is the area that we slowly start moving in, right? And how do we do this? We do a lot of physical activity, right? We move around our hands. So using what is called this nano generator, we can generate electricity, and that electricity is good enough to sense or power these sensors, right? Or also we have a sweat, right? And during the sweat, we also generate a lot of chemical. I said glucose, right? If glucose is converted into gluconic acid, I said there are electrons is being produced. Using that particular power also, we can power them. So there are people now very interested in what is called a flexible wearable device that is self-powered. Instead of using a battery, that itself should work. Either used on solar power or used on what is called the actions, that data that we do, because they are very useful to monitor lively the athletic activity. If anyone is going to get tired or going to fall down, we will be able to like tell them in advance. And that has been such kind of a sensor is what has been used in a spacecraft. The people who travel in a spacecraft, they use what is called these kind of self-powered sensors, because they don't have access to all the battery replacement and all, right? And that's the place where this gets very useful. Anyway, if you have any questions, I'll be very happy to answer, or madam can probably read me some of those questions that people talk about it. And how do we generate electricity is what has been given in this slide. Okay, thank you.
Thank you, sir. We sincerely thank our guest speaker, Dr. Palniyappan sir, for kindly accepting our invitation and gracing the occasion. Be inspired and enlightened by your keynote speech, sir. So we have received many questions in chat box. So we will open the session for discussion. So if any questions you want, please put it in chat box.
Yeah, someone I think is asking urine
Sir,
blood.
can I read the question, sir?
Yeah, please go ahead.
Yes, sir. You can also. Yes, sir. Yes,
Yeah.
sir. You can see, sir.
I think someone is asking about urine sugar, right? Yeah, I mean, our interest is not on urine, but that can also be measured using these electrochemical sensors, because handling of this human excreta is a problem, in the sense we need to get us permission from government to do such kind of system, and that is why it's not been at least handled in our lab. But very remotely, we do one or few examples and compare the sugar levels in urine as well as a blood. But then, we cannot really publish it for one reason is we need to get first prior approval and all, and that process is still going on. Yeah. You can write to me at palani112@gmail.com. I myself will type that in a chat box. If anyone has any question, they can contact me directly also, or they can put a question to Professor Krishnaveni ma'am, and then she will forward it to me. Either way, it's particularly fine with me. Yeah. How convincing is the impedance spectroscopy is another question asked by Professor Chetna. With respect to what techniques are, impedance spectroscopy is very, very useful when it comes to corrosion, because they talk about how much is the material or the coating is withstanding against a corrosion. It's talked in terms of resistance only. To very specifically for a biosensors, at least in our lab, we don't do too much of impedance spectroscopy. We'll do a lot of LSV technique or DPV techniques. I hope that answer your question. Yeah. What are the biosensors which are in practical applications? Okay, in a laboratory level, we have a sensors for cortisol. We have sensors for lactate. Only problem would be how to translate this into a gadget is what we've been working with the different industries. And there are people who are interested to convert these into gadgets, and we are closely working with them. Yeah. Okay, one good question is, sir, any studies conducted about human health impact of graphene? Yes. I mean, I'm using a carbon or graphene based material to purify the water. But then the next question would be, is this water is again contaminated with the graphene as such? Whatever in the laboratory studies we could figure out is very negligible amount of carbon material that comes into it, maybe a nanomoles level, and that is still, I would just say, compared to the risk that has been exposed with the heavy metals or plastics or bacteria, the level that with the carbon will be very low. Yeah, but that need to be definitely taken care in the coming days for sure. Yes. Yes, we can do a gold electrode, we can get a results, but then whenever you use any of these electrode as such, we call it as a modified electrode. Without modifications, you always looking at the potential for that particular system, whatever you want to do analyte, whatever you are looking at as an oxidation potential or reduction potential is going to be on higher side. So just to bring out this onset potential for that particular analyte is why we functionalize the electrode, whether it be a carbon electrode or whether it be a gold electrode or platinum. Normally silver is not used because it is very susceptible to oxidation that easily. Yeah. No, gold doesn't really interact with the water as such. I mean, you have a gold bangles and ornament, right? You can even take it as such. When you take a shower, when you wash your hands, maybe your bangles or your bracelets or your, um, necklace, they don't lose the shining property by throwing in water or a soap, even with a detergent. So gold is really inert material. You can use as an electrode. There is absolutely no problem. And that is why they've been used as an electrode material, because they're not susceptible to oxidation, except aqua regia. If you throw in aqua regia, of course, they will dissolve. Yeah. Can graphene be used in concrete? Yes, depending on the purpose. There are a group in our institute which is called corrosion divisions, and those people are using graphene for different purposes, and they'll be more appropriate to answer that question. Just probably limit my answer to that level. Yeah, it can be used. Yes, to answer very directly, that can be used. In corresponds to graphene, does fluorine has the same impact or higher? That is one question again put by Dr. Chetna. I mean, now they figured out graphene is probably much better than fluorine, because synthesis of fluorine is very expensive and their applications are limited. People are slowly moving from fluorine to graphene. From fluorine, we actually moved on to carbon tubes, nanotubes. From nanotube, now people are being slowly concentrating or focusing towards making graphene, because making graphene is a lot easier compared to making a fluorine, and that's the only reason I would put it that way. Yeah. There is one question on what about silver nanoparticle impact. I don't know with respect to what, I'm not very sure. Right. Okay. I mean, the rest of the questions we could answer, or someone can send an email.
Fine, sir. Fine, sir. Thank you, sir. Thank you, sir.
Thank you.
Now I request our HOD, Department of Chemistry, Dr. Manjunath, sir, to propose vote of thanks.
Thank you, ma'am. Good afternoon, all. I deem it is a great honor and privilege to propose vote of thanks on behalf of Department of Chemistry, Don Bosco Institute of Technology, on this memorable occasion. First, we would like to thank our beloved management for their continuous support for organizing the events. We thank our beloved principal and vice principal their continuous support for organizing this FDP. We thank our today's chief guest, Dr. Palaniappan sir, CSS Sikri Karaikudi, who, despite his busy schedule, has found to grace this inaugural function of faculty development program and enlighten our participants in the area of electrochemical sensors. Thank you, sir. I owe special gratitude to all the eminent speakers for accepting our invitation for delivering a talk in their busy schedule in our FDP. We thank my department colleagues for their active involvement for organizing this faculty development program. And we thank all the participants for your gracious presence and continuous support for organizing this FDP till completion of the last sessions. Thank you all.
Thank you, sir. I think someone asked about the difference between 2 and 3 electrode. It's very simple, just to put it in a shorter way. You miss this reference electrode when you use a 2 electrode system, right? So just to incorporate the reference electrode only, we are using a 3 electrode system. It's very useful in terms of developing a biosensors, because you can see small current amplification. We will be working with a nanoampere or less than that. If you have a very less amount of analyte, the current that will be produced will be very, very small, right? And just to magnify that current only, we use a 3 electrode using a reference electrode. So that we will be able to...
feedback link.
Yeah.
Thank you, sir. As a token of love and appreciation, we would like to share appreciation certificate. Please accept it, sir. E-certificate.
Okay, ma'am. Yeah.
So it was a very informative and very much interactive session, sir.
Okay. Thank you, ma'am. Thank you. So shall I leave now?
Yes, sir. Yes, sir.
Yeah.
You can leave,
Yeah.
sir.
Okay.
Thank you so much, sir. We will mail you, sir. We'll mail you the certificate, sir.
Yeah. No. Okay.
Yes, sir.
Oh, thank you
Thank
for the
you so
certificate.
much.
Yeah.
Yes, sir. Thank you so much, sir. Yes, dear participants, thanks for patient listening. And feedback link is shared in the chat box. Feedback link will be shared only in the chat box, not in the WhatsApp group. Certificate will be issued on the basis of feedback as well as attendance. And next session is going to be start by 2 o'clock. And the topic of role of advanced functional material in modern electrochemical energy storage system by Dr. Satish. So that please do join 2 o'clock sharp. Thank you so much. So with this, we are ending the session. Once again, I'll repeat. Feedback link will be shared only in the chat box.